Okay, so this is a video lecture for Math 1133, Calculus for Business for UTSA. And yeah, let's just jump right into it. So in Module 1, we're just reviewing some algebra prerequisite material for the class. And basically, I modeled this after the first homework assignment in WebWork so that you can kind of just go through this and do the problems as you go. They're in the order of the homework, right? I'm not going to do every problem, and I'm not going to go into every detail of everything on every problem. I might skip some stuff. I might not go into detail that you need. So if there's something you don't understand, send me an email. We can get on a Zoom call, and I can help you figure it out. Yeah, so let's get started. So the first thing to talk about is domain and combining functions. So I've got two functions here, f of x and g of x. Oftentimes you'll be given the domain. You'll be told, okay, here's your function, f of x equals whatever, and then the domain is some interval, x goes from 0 to 10 or something like that. Sometimes you're given the domain, sometimes you're not. So when you're not explicitly given the domain, your standard assumption is that the function will accept as an input any number that doesn't otherwise cause a problem. Okay, what do I mean by that? Well, if we look at this function, f of x equals 2x squared, whenever I plug in a number for x, let's say 5, 10, or 100 or whatever, well, the first thing we're going to do is square that number, and that always works. You can square any number, right? And then we're going to multiply by 2, and you can do that with any number. So if I put in 10, 10 squared is 100, and times 2 is 200, right? And no matter what I pick, I can put in any number. It'll always work. So the interval version of this, well, we could say like this, x is any real number. That is one way to say this. X is any real number. You can use a number line to indicate which numbers are allowed. Like if you think about, say 0 is here in the middle, right? And negative numbers are like over here, and positive numbers are like over here. Well, we could say, well, since x is any real number, then you just kind of shade in the whole number line to indicate you're including everything, which is sort of redundant. Like, why even draw it if it's everything, right? So oftentimes we wouldn't do this. The interval version is comes from thinking about the graph of the number line and thinking about all the way on the left, negative infinity is all the way to the left on the number line, and then positive infinity is all the way to the right on the number line. So when you refer to the interval version of the description of the domain, this will be negative infinity with a parenthesis, because you use a parenthesis to start the interval when you're not including the value. And since negative infinity is not a number, you can't plug negative infinity into f. We're not including it because it's not really a number. Okay, and then up to positive infinity, and we'll use a closed parenthesis to indicate that we're not including infinity. Okay. Coming over here to g of x, well, now when we pick various numbers for x, we're going to run into an issue potentially. So if we think about plugging in, say 0, well, let's plug in 3. If we plug in 3, right? G of 3, you plug in 3. 3 plus 6 is 9, and the square root of 9 is 3. So we'll get a result that way, right? If you plug in something like, say, negative 2, right? G of negative 2, let me do this in a different color here. I'm going to erase this part in a second. G of negative 2, well, that's going to be the square root of negative 2 plus 6. That's the square root of 4, which is 2. You get an answer that way, right? But if you pick the right number, like, say, negative 7, then it doesn't work. Let me erase that. If you pick negative 7, so G of negative 7, okay, well, you're going to have the square root of negative 7 plus 6, and negative 7 plus 6 is negative 1, so you have the square root of negative 1. And you might already know where this is going, but perhaps not. So the square root of negative 1 is not a real number. There's no number you can start with, no real number that you can start with and square it and get negative 1 as a result. You can't do that, right? So this is what's called the imaginary number I, and at least at the undergraduate level in business classes, there's going to be, obviously, like accounting has arithmetic, of course, right? Finance and economics have some more advanced stuff, and you're going to probably see algebra at some point in most not math degrees, but business degrees. There's going to be some algebra at some point in some class, right? Well, imaginary numbers really just don't show up because none of the uses for algebra and arithmetic, algebra, and calculus, none of the uses in finance or economics or business in general, none of them require complex numbers, imaginary numbers. In science, they do. Physics, chemistry, biology, these all use complex numbers for various reasons, for various applications, and especially physics and chemistry use it a whole lot. Quantum mechanics cannot work without the concept of an imaginary number. You need it to do the calculations, and electrical engineers require it to do their calculations. So we're going to say that this doesn't work, that -7 is not in the domain. It doesn't work because, well, you don't get a real number as a result when you plug into the function, okay? So what we want to think about is, what is the first number that does work? Well, basically the inside, the x plus 6, this needs to be at least 0 in order for the result to work, okay? If you plug -6 into this function, okay, then you'll get the square root of -6 plus 6, which is the square root of 0, which is 0, so that checks out. So -6 is a valid input. So if you put in anything smaller than that, or less than that, I should say, like -7, then it doesn't work. Or -6.5 doesn't work. -6.1 doesn't work. So when I solve this inequality that I set up, I'm going to get the 6 is going to show up. So if I subtract 6 on both sides, I'll have x is greater than or equal to -6. The -6 comes from setting the inside up with an inequality and getting x by itself, and then you get this inequality. So x is any real number that is greater than or equal to 6. Like this inequality could be rephrased in plain English, right? X is greater than or equal to -6, if you want to say it that way. But I won't write it that way. It's like, we don't need to do that. Now, the number line version of this, I'm going to mark -6 in the middle, just because that's the number that I have that I'm talking about. You don't have to put 0 in the middle for a number line. Now, notice that x is greater than or equal to -6. So x could be -5, -4, -3. Those are all values that are over here to the right of -6. Like 0 is maybe like right here or something, right? And then like -4, well, now my scale is off, and I wrote 6 instead of 0. Let's put it here. Like -4 is here, -2 is here, right? Those are all included, right? So now I'm going to put a filled-in dot at 6, -6, I mean, because of the greater than or equal to. The or equal to part means that -6 is a number that we're talking about, and I'm going to shade to the right, which I guess I could be using like that green coloration for that, but whatever, I'll just do that. And I want to think about having infinity all the way at the end of the number line. So my interval starts at -6, and I use a bracket because I'm including that. That's just the standard notation, parenthesis for when you're not including that value, and bracket for when you are including that value. And then this goes all the way up to infinity, includes all the positive numbers as well. Okay, so that's how you find that's the overall process of finding the domain of a function that when you're not given the domain up front. The standard assumption is, well, you're gonna have all real numbers that work, and how you determine those is, well, you're gonna have to think about what numbers when plugged in would cause issues. And sometimes you can do that by guessing and checking and building a list and drawing a number line and marking things down, what works and what doesn't when you plug it in. And then also there are some standard ways, like if you have a function with a radical, the square root of something, we'll take that inside part, form an inequality, and then solve that inequality, and that will get you the result. So that's just find the domain of a function. Now, what if we had some combinations of functions? Like if I want to say, oh, well, what about, how do I form the sum of the two functions? And then how do I form that domain of the sum? Okay. So if I'm adding f of x to g of x, that's what this says. F of x plus g of x is another way of saying that. It kind of looks like we're distributing the x, but that's not really what's happening. It's not called distribution. This is just, these are equivalent. The left-hand side is just shortcut notation for saying this right here. But there's no distribution involved here. It's not like we're, like if you have like, you have 3 times x plus 1 and you distribute, you have 3x plus 3, right? You apply the 3 to both terms. That's not what we're doing there. It's purely a notational thing. I probably could have glossed over that, though, and not mentioned it. Anyway, so when you combine two functions, the new domain it comes from the new domain is inherited from the prior domains, the original domains, and how you combine them depends on some things. There's some things you gotta watch out for. In general, what you're gonna find is that you want what's called the intersection of these two. Because in order for this function, f of x plus g of x, the combination, to be defined, well, you pick a number, plug it in for x in f of x, and then it has to work. You have to get a number, a result that way. And then also plug it into g of x. You have to get a result that way. So if you pick -7, right? Well, then I'm going to have f of -7, which does work, right? We didn't check that number specifically, but you can square any number. We talked about that. And then you're going to have plus g of -7. But we already figured out that g of -7 doesn't work, okay? So really, since the domain is all real numbers, anything is acceptable, you're pretty much only restricted by the domain of g. That's the one with the limitation involved. So the intersection of those two is like, well, what numbers are on both lists? The intersection of those two, since the left one, which I was marking, but now I've unmarked. I mean this by the left one. This has no restrictions, so you just have these restrictions. So the intersection is that interval, -6 to infinity. Let me clean this up a little bit. Okay, so domain, this is -6 to infinity. And for the most part, that's what it'll be. So these other ones we're going to look at, that's for the most part, that's what it'll be. That's what will be accepted. There are exceptions to that. There are complications to that, but we're not going to have to deal with them that often. So let's just go ahead to the next one then. So this one here, this says f times g of x, which is really just f of x times g of x. Again, this is not like distribution or anything. This the original version that I'm working from, that's just a shortcut notation for what I just wrote. So for this one, again, if you plug in a number like say 4, right? Well, then you're gonna have like, well, f of 4 times g of 4. That's a times, not a, yeah. Right? f of 4 times g of 4. Well, we know that f of 4 is defined, right? Because any number works. And we know that g of 4 is defined because 4 is greater than -6, so it works. And basically, you run into the same limitation. The only thing that does not work is stuff that is not in this interval. So the domain's the same thing. And I didn't put it on here, but we'll do another one, because there is a complication that is not going to show up with any of these, but we'll talk about something. Another example in a second. So now let's look at this one. This one you might not recognize. This one says f composed with g. It's like f of g. And that little O thing, this is not really like a letter. It's just called the circle notation that means function composition. It's not like from the word of f of g. I don't think, though maybe it is originally. Anyway, it's just a symbol that means put g inside of f. So this, another way to write this is f of g of x. Okay, and I actually prefer this notation to this notation for the most part, but they mean the same thing. Now this gets a little squirrely. Oh, you know what? I left something out. See, this is one of those things that if I were trying to be more professional about this, I might start over, but I'm not going to start over. I want to write out just literally what this is. This is 2x squared plus the square root of x plus 6. Sorry about that. I just forgot to do that. And then this one, this is 2x squared times the square root of x plus 6. It doesn't really illuminate what we were talking about, but I kind of need to do it for the next one, and I kind of meant to do it for all of them. Okay, so f of g of x, what that means is we're going to plug g of x inside of f. So f, well, that was 2x squared. So this is 2 times the input squared. Whatever the input might be, well, that's the square root of x plus 6. Okay, let's write that a little bit neater. X plus 6. Okay, so g is plugged into f, the function. Now we can simplify this a little bit, and what do I mean by that? Well, excuse me. So if you have something like this, you have the square root of, say, 5. Okay, and you square it. Well, that means that you have the square root of 5 times the square root of 5. And you might see where this is going, but perhaps not. So I'll assume that you, the viewer, doesn't quite see where this is going yet. if you look at this, you might be thinking about 25. Well, if I have the square root of 5 times the square root of 5, isn't that the square root of 25? You multiply the insides, which is true. This is the square root of 25. And then you might notice, oh, well, that's just 5, right? The square root of 25 is 5, okay? So really, this way of thinking is what I see a lot. People will think through it in these terms because they're thinking about using properties of roots and radicals to combine things and then simplify afterward. What I want to point out, though, is that this symbol, square root, it means the thing that if you square it, you get 5. That's literally the definition. The thing that if you square it, you get 5. And by thing, I probably mean number, the number that when you square it, you get 5. But we'll say thing. Thing that when you square it, make that neater. You get 5. Well, if we're squaring that thing that makes 5 when you square it, we get 5, right? Like, we don't need to think about the 25. If you recognize that the square means throw out the square root, you just have 5, then you can simplify this kind of thing a little bit more easily. So over here, this is saying that this square root of x plus 6, by definition, that is the thing that if you square it, you get x plus 6. So the square cancels the square root. There's potentially more to it than this, and we'll deal with that as it comes. But we can simplify this. This is 2 times x plus 6. Or if you want 2x plus 12, if you want to do that. Now this might be a little, this might, you might go the wrong direction from here. Let's put it that way. When you look at this, you go, oh, well, now the domain is all real numbers, right? Because you could plug in whatever. So that means that f of g of, like, say, -7, right? Oh, well, that's just going to be 2 times -7 plus 6, and you get a -2 as a result, right? That's great. It works out. The answer to that is no, it doesn't. Because the limitation on what this x is allowed to be can't be -7, right? That limitation doesn't go away when the root symbol and the square, the exponent, go away together. They cancel each other out. That limitation remains. So the domain here still is just -6 to positive infinity. Okay, so you have to be careful when you are reducing and simplifying not to forget about that. That will be important sometimes. The sort of the problem with that is it's usually not important, but then it sometimes is. So you have to think about it all the time anyway, because if you don't think about it, you're not going to notice it when it does matter. So we have to always be aware that the domain is inherited from the pieces, and the domain doesn't get bigger when you combine functions. It gets smaller because if you think about, well, what's a good example? I don't have a good example off the top of my head, but when you have restrictions from two different sources, they don't let's put it this way. Say your mom has rules for you, right? You're only allowed to do this on Thursday and you can't stay out late on Friday. There's all these rules your mom has. And then there's all these rules your dad has. And they aren't the same rules, right? It'd be kind of nice if they were, but they aren't the same rules, right? Dad's more permissive on certain things than mom is. But you're kind of beholden to both, right? And so really, when their rules are different, you get stuck having to follow two sets of rules and having to make sure you're following both of them, right? It's kind of like that. You've got more than one set of rules, and you have to abide by all the rule sets you've got, and you can't ignore one just because the other allows it. So just because f will accept any number, you have to be careful still because g doesn't. Okay, and g sees a number before f does, which complicates things even further sometimes. Again, when this comes up in the future, if you're dealing with a composite of a function and you're not sure how this applies to that, just send me an email. We'll get on a Zoom call, help you figure it out. There's always going to be, it's hard to give a full comprehensive treatment of here's how this will always go down because it depends on the context, depends on so many things. Anyway, let's do one more example of this because I had thought of one that would actually be quite good. So let's do f over g of x, the quotient, not equals, of x. The quotient of the two functions, okay? This is just a shortcut way to write f of x over g of x. the fraction, like a literal, you're doing division. Okay. So this would be 2x squared over the square root of x plus 6. Not 2 plus 6. Sorry. So you might think, oh, awesome. That means it's just going to be like, it's kind of like this one. Like instead of multiplying, we're dividing. So it's going to be kind of like this. And also, these have all been the same. So you might think, well, it's just going to be the same, right? Well, not quite. Because think about what happens when you plug in negative 6. If I do f over g of negative 6, well, that's going to be 2 times negative 6 squared. And of course, feel free to pause the video and think about this. If you think you know where this is going, you can pause and then unpause. Okay, so what's going to happen is we're going to get 72 on top, right? Negative 6 squared is 36 times 2 is 72. And then on bottom, we're going to have the square root of 0, right? But that's 72 over 0. Oh, no. You can't divide by 0, right? So when you have a fraction, when you're dividing, you have to be careful because anytime the bottom would be 0, that's what you're not going to be allowed to use, okay? So if I can, another way to say that is just take the denominator, set it equal to 0, and solve that equation. And you put like a slash through it, it's not allowed to be 0. And then you can figure out what number causes that to happen. I'll skip doing that because maybe it's obvious at negative 6 because we've talked about this enough. Negative 6 is the number that does that. So for this one, the domain, this does not include negative 6. So the fact that we're dividing created a new restriction, and negative 6 no longer works. Okay, so that's how you form composite functions or combinations of functions. This one here, this one's called composite. It's function composition. These are just other different ways of plugging the functions, putting the functions together. Whereas this one is called a composite. That's the term for it because one is plugged into the other. Anyway, so there's that. Moving along. So evaluating functions. This is going to be really important for the rest of this course. Well, I say the rest of this course. For a big chunk of the class, this concept will be very important. So we're going to start with a really simple linear function so that we can focus on the most relevant parts of evaluation and substitution, and not worry about like dealing with exponents and roots and stuff like that. So we'll do a simple equation here. So f of x equals 3x plus 4, and then I can plug in 2 for that. So this will be 3 times 2 minus 4, so that's 6 minus 4, just 2. So maybe that part was easy, okay? You can also plug in a whole expression that has a variable, and what you basically do is you take this x plus 2 and you plug it in wherever there's an x. So f of x plus 2 will be 3 times, in parentheses, x plus 2. I use the parentheses for grouping so that the plus 2 gets every modifier it's supposed to get, okay? And then minus 4. So this is not, I want to be very clear, this is not 3x plus 2 minus 4. That's wrong, because the 2 is supposed to be inside some parentheses with the x. That's actually correct. So I'll go back and rewrite it in the right color. Okay, so this is 3 times x plus 2 minus 4. And we can, if we want, we can distribute 3x plus 6 minus 4, so 3x plus 2. Coincidentally, we get a 2 still. So that's if you're plugging in an expression with x, you just plug it in wherever there's an x in the original function, you put in that substitution piece, whatever you're plugging in. Usually you're going to need parentheses. Sometimes you don't need it. Sometimes you do need it. So I tend to just put the parentheses every time. Even if it feels redundant, I usually go ahead and do it anyway, just so I don't miss it when it does actually need to be there. Okay, so negative a. Well, we're going to take negative a and plug it in where x is. So 3 times parentheses negative a close parentheses minus 4. Okay, and if I want, I can simplify that a little bit. This is negative 3a minus. I accidentally stopped the recording. Don't know why. I think I just hit the space bar on accident. So yeah, so we had just worked out plugging in negative a and then multiplying out 3 times negative a makes negative 3a. I don't know if I'll be cutting this piece out in the editing the video later. Anyway, moving along. So now f of a plus h. So we're plugging in 2 letters, a and h. And what h and a are for now doesn't matter so much. Next week in the class, well, maybe next 2 weeks. Is it module 2 or 3? Anyway, in the near future, we'll be looking at, okay, what are these a and h things? What do they do? Because they represent something, but we're just not ready for that yet. Okay, so this is going to be 3 times a plus h in parentheses minus 4. Okay, so that's going to be, if I want to distribute 3a plus 3h minus 4. Maybe I don't need to distribute, it depends, but that's basically how that goes. Okay, so that's evaluating functions with different types of inputs. You just plug in the input using parentheses. Sometimes you need it, sometimes you don't. Again, I just kind of do it all the time. Okay, next thing. The next thing is called the difference quotient. Okay, and so the a and the h show up again, but this is a little bit more complicated. We have this big messy fraction with lots of stuff going on. So this represents something, and I won't talk about it yet, but we're going to need it for calculus I think it's the end of module 2 or the beginning of module 3. My memory on that is fuzzy, but it's something we need for calculus. So there's a couple of ways to get started. I find that maybe the best thing is to focus on working out what f of a plus h is, and then subsequently forming the entire numerator and combine like terms and everything as we can. And then lastly, putting it all together in one big fraction and simplifying as much as we can from there. So it's kind of like 3 stages that I do this in. You don't have to do it this way. And when we do more examples later, you'll see that sometimes we can't do it this way. You'll see more later. So let's work out what f of a plus h is. Okay, so f of a plus h, well, that we're using this function. That's going to be 3 times a plus h squared minus a plus h. And notice that since we had x in 2 places, we now have a plus h in 2 places. Okay. So I'm going to FOIL this out, and I'm going to cut corners a little bit, maybe. So let's do this. So this is 3 times a plus h times a plus h. I decided not to cut very many corners. Minus, let's just do a plus h. We'll do one step at a time. Since it's the first time we're doing this, it doesn't hurt to show every detail. So now I need to FOIL these guys. Okay, so remember FOIL stands for first outer. That could be written more neatly. First, outer, inner, and last. Okay, so the first part refers to the fact that we're going to take the 2, oh, wrong tool there. We're going to take the first thing here times the first thing here. Okay, when we're foiling, I'm focusing in on, for now, just these guys here. I'm foiling a plus h times a plus h. Okay, maybe that wasn't obvious already. So that's a times a, so a squared. Okay. And I'm using parentheses because the 3, it's kind of like there was another set of parentheses here, and the 3 applies to everything after it, not the minus part. So I'm putting those parentheses so we keep track of that. We don't lose track of the fact that the 3 applies to the entire group, to the left of the minus sign. Plus, well, outer, that refers to the things furthest from the center, from where the 2 parentheses right here are forming the center. Okay, so a times h. Or just AH, plus inner refers to the 2 that are closest to the center, so H times A. And when you have a product of 2 things, the order doesn't matter. So H times A, this is the same as A times H. So if I want, I can go ahead and write it that way. I'm going to go ahead and write it as H times A for now, but we need to remember that HA and AH are the same thing. And then the next part which I guess will be plus something. Sometimes it'll be minus. In this case, it is a plus. So last is the last item in each pair. H times h is h squared. Okay, and then I'm going to distribute this minus sign onto both terms. So minus a minus h. Okay. Oh, I forgot something. What did I forget? I just got done talking about it. This open parenthesis needs to have a closed parenthesis as well, before the minus specifically. So sorry about that. Okay, and then I can distribute this minus, not minus, sorry, but this 3, I can distribute onto each one of these. So I'll have 3a squared plus 3ah plus 3ha plus 3h squared. But, before I do that, let's combine like terms. Like we said, that these are really the same thing. ah and ha are equal. So I really have 2 copies of the same thing. So this is 3 times a squared plus 2ah. Got ah plus ha, that's 2 copies, 2ah. Plus h squared minus a minus h. And then the 3 can distribute. So 3a squared plus 6ah plus 3h squared minus a minus h. So there we go. That is f of a plus h. Foiled, simplified. There's no like terms to combine. Okay. Like this, we have one term that has a squared. None of these have a squared. We have one term that has both a and h. None of these have both a and h. And this is h squared. Neither of these have h squared, and so forth. So there's no combining of like terms. So now what we can do is form the whole numerator, f of a plus h minus f of a. So I'm going to take this entire thing and copy that first. Okay, and then minus, because of this one, f of a. Okay, well, that's going to be 3a squared minus a. Okay, because the original function was 3 times your variable squared minus your variable. So if I plug in a, I'll have 3a squared minus a. Now I have to be careful. I'm going to intentionally do this wrong and see if you can see what's wrong with it. Okay, it's a somewhat subtle thing, but basically what I've done is this minus, we're subtracting the group f of a. This minus is not affecting that a, and it should. So either I need parentheses to indicate I'm applying the minus to the whole group as I should, or I can go ahead and turn that minus into a plus right here. And that takes care of that minus distributing to the a as well. And how I do it is up to me. I'm going to go ahead and just turn that into a plus right now. So I've handled this while plugging in a in one step, which is fine if I want to do it that way. So there's the whole numerator. Now you might notice that we've got stuff like this. We've got minus a and plus a. We've got plus 3a squared and minus 3a squared. So those are all going to cancel. And you'll notice probably that every term that's still left has an h in it. This is supposed to happen. If you're doing one of these and you end up at this stage and you have a term with no h, like you just have like a plus a or a plus 5 or something like that, then you've got a mistake. Every term should have an h present in it at this point. So now we can form the entire fraction by putting all that over h. Okay. So big fraction f of a plus h minus f of a all over h. And then 6ah plus 3h squared minus h all over h. Okay. The next thing to do is to factor the numerator, because what's a somewhat common mistake is to go, oh, awesome, h's cancel. The h on top that I just marked out as canceling is not available for cancellation because it's not a factor of the numerator. It's added or subtracted with this other stuff, subtracted in this case. So this h just is not available for cancellation. It can't. The h on bottom is ready to cancel, but the h on top is not. So what I have to do is recognize that every term in the numerator does have an h and factor that h out. So from this term, I'm removing an h, so the 6 and the a will remain. From this term, I'm removing an h, so the 3 and the other h will remain. And from here, I'm removing an h, and it might not be obvious why. And if it's not, maybe you think about it, you figure it out, or we get on a Zoom call, I help you understand it. When the h here gets removed, I have a 1 left over. One way to think about it is basically I'm dividing h out of each term, and negative h divided by h is negative 1. Maybe that's sufficiently clear. Okay, so this will be h times 6a plus 3h minus 1 all over h, and now the h that we factored out, that one can cancel. So this h on top, this is available for cancellation because it's been factored out of everything, and so every term in the numerator gave up a copy of h to contribute to factoring, and then now that one is available for cancellation. So then we just have 6a plus 3h minus 1. And that's it. That's our answer, which might be unsatisfying because you might think, well, wait, what? what did we calculate? What did we get? It doesn't feel like an answer. But that's the point of the difference quotient. We haven't gotten to what it represents yet. So in a week or a week and a half, 2 weeks, whatever it is, we'll go over, okay, well, what is this for? What is this doing? Why do we, what is A? What is H, right? What are these things? We'll talk about that later. For now, it's just the algebra of getting it done. So don't worry about the answer being meaningful yet. We're going to use it for something later. So don't worry about that. It will attain some meaning. Okay, moving along. So the next thing is, this is sort of an application problem that incorporates several different concepts that we're going to need. So I didn't write out like a whole paragraph, but this would typically be a part of an application problem about like supply and demand, that kind of stuff. So this is about maximizing revenue. And this equation, P equals 55 minus 0.011x, this is relating the price of some widget to the demand X in thousands of widgets. So, if you want to talk about, oh, there's a demand in this market for this widget, and the demand is 5,000 widgets, well, then X would be 5. Okay, so when you're doing application problems, you have to pay close attention to when a variable has a scale attached to it. X is in thousands. So if X is 3, that means 3,000 is really what we're dealing with, okay? And then P is price in US dollars. And in a homework problem, it might be in hundreds of dollars or thousands of dollars or millions of dollars. In that case, you have to pay attention to that scale. In this case, it's just price in dollars. So when P is $5 is what we're talking about, okay? So this equation relates the price of the widget to the demand of the widget, and we're going to maximize revenue. Well, revenue is not quite here yet, but one way to think about revenue is, like if you were selling, like say 100 widgets, and if you don't know what a widget is, basically it's like a doohickey. It's a thingamabob. It just means we're talking about something in economics, and we don't care what the thing is specifically right now. We're talking about things around it, the context of it. We don't care. Is it a car or a toaster or a phone? We don't care. So we call it a widget because it doesn't matter what it is in the moment. Okay. So if you have 100 widgets that you're selling for like $5 each, I think it's pretty clear that your total revenue, well, that's gonna be $500 because you sold a $5 thing 100 times, right? You just multiply them together. So the revenue is always going to equal the price times the demand. Okay. And remember, X is in thousands, so we're going to have to keep that in mind as well, okay? So this means that R equals 55 minus 0.011x times X. So that's going to be 55x minus 0.011x squared. Hold on a second, I have to close a door. Okay, I'm back. Now, when we do this, we have to keep something in mind. So remember how X is the demand in thousands, and then the price is price in dollars, right? Well, if the price, suppose for a second, is like, I'll just make up a number, like $8, right? And X is 10. That means we're selling 10,000 times $8 is $80,000, right? So because we have a product here, this R, this is now in thousands of US dollars. Probably should spell thousand right, though. Thousands of US dollars. Sorry about the handwriting. Thousands of US dollars. So, well, we have to keep that in mind. Nothing up here said that the dollars were in thousands, but because we're doing dollars times something that is in thousands, now R is also in thousands of dollars. We have to be careful about that. Okay, it would be easy to overlook that. So we get this this quadratic function that describes the revenue. Let's talk about how we're going to maximize it. Later in the class, we're going to look at how to maximize just any function using calculus. But when you have a quadratic function, there's one specific way to do this. So if you have some parabola, right, that is like, say, like that, okay, just to make something up. There's a high point here, right? There's a maximum, right? This is called the vertex. And usually the letters H and K are used to represent the horizontal and vertical coordinates of the vertex, okay? If you have this as, say, like y equals ax squared plus bx plus c, the general form of a quadratic function, well, oh, and I probably should adjust this slightly. A little bit bigger, and then fill that in like right there, okay? Well, you know how you can get the x-intercepts? You might know this, and we'll talk more about intercepts later at some point. You know how you can get the x-intercepts here by using the quadratic formula? Oh, if you set this equal to 0, 0 equals ax squared plus bx plus c, right? And then by using the quadratic formula, you know, x equals negative b plus or minus the square root of b squared. This is going somewhere, I promise. Minus 4ac all over 2a. So this one over here, this is, on the left, this is negative b minus the square root b squared minus 4ac. It's getting hard to read. Let me rewrite that. This is negative b minus the square root b squared minus 4ac all over 2a. Okay, and then this one is negative b plus the square root of b squared minus 4ac all over 2a. And this drawing is assuming that a is positive, but in this case, you know, or that a is negative rather, but that's fine. I'm not going to worry about that right now. I might actually have these backwards, but because I don't have numbers, it's hard to tell, right? These might actually be backwards, but I'm not going to worry about that right now. In between them, in the middle, that's this x coordinate here that sits right below the vertex. This is the value of h, would be that horizontal value, right? Well, it turns out that horizontal value comes from taking this quadratic equation and tossing out the square root part and just taking, oh, well, it's negative b over 2a, okay? So you can always calculate the vertex using the coefficients of the quadratic function, okay? And then k, you just take whatever h is and put it back into your function. We never called this f of x. Sorry about that. Let's call this f of x. So k is just f of whatever h was. You just take that x, the x coordinate, h equals negative b over 2a, plug that back into your function, and you'll get the vertical coordinate as well. So we're going to use this formula for the horizontal coordinate of the vertex in order to find out, well, what's the maximum of this one, okay? And notice how this this coefficient on the quadratic term is negative. That's what makes it shaped like this. If that number were positive, then instead the graph would be shaped like that, and it would have a minimum, not a maximum. But in our situation, it's a maximum. So what I have to do is be very careful to identify the coefficients properly. Remember that the format was f of x equals ax squared plus bx plus c. And that doesn't mean that this is a and this is b, because they're not in descending order. If I want to identify them as a, b, c, one way to do that is to rewrite this function over here in descending order, putting the quadratic term first. So let's go ahead and do that. It's not the only way, but maybe it's the clearest way to write it so that it's clear for everyone watching the video. So this is my A, and this is my B. Okay. Of course, you can, if you want, say, oh, well, A is the number on the x squared. That's this number. Oh, and B is the number on x. That's this number. Like you don't have to rewrite it to make that identification, but maybe it helps to do that. So that means that H, that's going to be negative B over 2A. So that's negative 55 over negative 0.011. Okay. The negatives will cancel. We have a plus over a plus. I noticed that, well, for one thing, I tend to avoid using the calculator until I really, really need it. So what I'm going to do first is multiply top and bottom by 1,000. I'm choosing 1,000 because the bottom number has 3 decimal places. Okay. So 55,000 on top, and then on bottom, 0.011 times 1,000 makes 11. And then also I notice, hey, 55, that's 11 times 5. So the top is 11 times 5,000 over 11. So then the 11s cancel, and I just have 5,000. Okay. So, yeah, maximize the revenue. Okay, so, sorry, just reading the question again, because you got to pay attention to the original question. So, remember, X is the demand in thousands. So, this is the demand in thousands. Okay, so really, the demand in total is 5 million. So in the homework, you got to pay attention. What's the scale of the variable? Okay. Now, if we want to say, well, yeah, but what revenue is that? Okay. We never called this. I called it R, but we could also call it R of X. I just said R equals, but that's fine. You call it R of X. That's not a problem. So the vertical coordinate of the vertex, this is going to be R of 5,000. Okay, we just plug it in, see what we get. So 55 is times 5,000. And keep in mind, this is in terms of thousands. So we're going to have to apply another multiplier of 1,000 a little bit later. Okay. So this one, I think I'm going to start reaching for the calculator at this point because this is getting a little messy. So so 55 times 5,000 is 275,000 minus, well, 5,000 squared, that's 25 million. That one's not hard. But times 0.011 is, well, that's weird. I'm getting 275,000. I feel like I must have a mistake here. Because how could that be 0? Because you're not maximizing the revenue at 0. So I've got a mistake somewhere. So we're going to find it, I hope. Let's see. So I'm going to pause the recording and see if I can find the mistake, and then I'll resume it in a moment. Yeah, I found the mistake. So maybe someone noticed it. It's right here. Probably someone's shouting at their screen, "No, what are you doing?" 2A, and then I only put A. I just put the 0.011. So this should be 0.022, actually. So we'll do that in red. So this should be 22. So this should be 11 times 2. The 2 will remain. So this is over 2. So this is really 2,500. Okay, so really the demand is 2.5 million. If you turn that back into widgets, not thousands of widgets. So that means that this is wrong. So this part I'll erase I'll erase all of this one, and I'll erase these, and we'll put in the 2,500 as it should have been the whole time. So yeah, I'm not going to edit this out. In the classroom, this is the kind of thing that might happen. And on an exam, as you may have noticed, it's in the syllabus. The exams are like free response. It's not multiple choice or anything. You have to handwrite your work, and then if you're in the online version of the class, you have to take a photograph and upload it. If you're the in-person version of the class, you're just in the class, right? So on an exam, if you make this exact kind of mistake, I might not take off very many points because like the technique is all right. You just made a silly mistake. If I'm looking at your work and I'm like, yeah, I could make that mistake, then I'm not going to like penalize you too harshly. I'll look at, okay, is the rest of what you did consistent and makes sense? Was it only just you made that little mistake where you lost a 2? Is that the only mistake? Okay, then, you get 9 out of 10 or something like that. So don't stress too much when you have these huge problems with all these steps. Since the tests are not multiple choice, I'm going to look at your actual work and then look for reasons to give credit or take points or whatever it is. So if it's like a really minor thing and everything else is done right, then you're going to be fine. Okay, but I do need the calculator for this. This is actually even harder now. Okay, so 55 times 2,500. So that's 137,500 minus 2,500 squared, which is 6.25 million. That times 0.011 is 68,750. Which, when you subtract that, that's 68,750. But remember, this is in thousands of US dollars. So really, the revenue is not $68,750. The revenue is really $68,750,000. Okay, so you're doing these application problems. You have to pay close attention to what is the scale of the variable, so that you're not. There's a big difference between $70,000 and $70 million, of course. So if you're putting in the wrong answer into WebWork because you overlooked one of those things, well, it's just going to tell you that it's wrong. So WebWork won't tell you, oh, you're off by a factor of 1,000. That WebWork doesn't have that capacity. So you need to pay attention to that. On an exam, if you were to forget this last part, I wouldn't take off much, maybe 1 point out of 10, something like that. It's relatively minor, but you need to pay attention to that kind of thing. Okay, moving along. So solve an equation involving exponents. So there's a lot going on in this example. I'm probably going to talk about a few things a little bit, as far as like the motivation and the why of some things. I'm mostly going to focus on just here's how you solve it. And then if you need help with extrapolating that to other problems and you're just not getting the why, so it's hard to apply it to other problems, then we can get on a Zoom call and I'll help you figure it out some more. So the first thing to notice is, we've got like this negative number here, okay? And then we've also got a fraction here. So I want to talk a little bit about the connection between fractions and negative exponents, okay? So off to the side, little sidebar over here, let's talk about exponents just a little bit. So this is something that's underlying what exponents are doing, but I think it can illuminate a number of the different properties of exponents. So let's say we had something like, say, 2 cubed, right? And the 3 in the exponent tells us how many 2's we have multiplied together, okay? Now, if I were to put like a times 1 at the end, that doesn't change anything, right? When you're multiplying by 1 doesn't change anything. Kind of like when you're adding, like if you have like 2 plus 2 plus 2 plus 0, when you add plus 0, you're not really doing anything. When you multiply times 1, you're not really doing anything. So in math, in algebra, I guess, there's more than one kind of nothing. Like if nothing's happening, well, there's more than one way for nothing to happen. You could be adding nothing, you could be multiplying nothing, right? And then 1 and 0 are what counts as nothing depending on the operation that you're doing. So keep that in mind. So there's that times 1, not plus 1, that times 1 hanging out the end here. So then if I have like 2 squared, well, that just means, well, I have 2 copies of 2, right? And then the 1 is still hanging out. And if I have 2 to the first power, well, I have 1 copy of 2, and the 2 is, or rather, sorry, the 1 is just kind of hanging out there, okay? And then 2 to the 0 power, you might be able to predict, well, each one of these, the exponent tells me how many 2's I have, but then there's always a times 1 at the end. And it turns out that for the same reason where I was saying how when you multiply by 1, nothing's really happening, because exponents are about multiplication. When you are not multiplying anything, what's still there, the placeholder is 1. Okay, and it's that same one that was there on each one of these. It's just hanging out at the end, not bothering anybody, and it's still there. When no one's around, the 1 is still there. Okay. Another way to think about this is as you go from row to row. So when I go from this row to this row, I can think about I'm going from 8, right? Because 2 cubed is 8, to 4, because 2 squared is 4. I can think about it as, well, I'm dividing by 2 as I go from one line to the next. And then from 4 to 2, I'm also dividing by 2 to go from 4 down to 2. And then from 2 to 1, I'm dividing by 2 again. Okay. So if I continue this pattern and say, well, what if I had an exponent of -1? It's not that I'm not multiplying anything, I'm unmultiplying a 2, right? Well, unmultiplying is dividing, right? When you're undoing multiplication, you're doing division. That's what this pattern here is. Each step, as we are reducing the number of 2s, we're multiplying up. Well, it's like we're dividing a 2 to go from one line to the next, because we're removing one of those copies of 2. Well, then when we get into negative exponent territory, we continue that pattern. So 2 to the -1 power, this is 1 over 2. Okay, the negative in the exponent doesn't mean you have a negative value. It means the minus symbol is used for lots of different things, and the minus symbol means the opposite of something. And often, like -5, right? -5, this is the opposite of +5. And typically, we don't need to write the plus all the time. Just 5 by itself is assumed to be +5, right? But when you put a minus sign in front of it, that's the negative of 5, okay? Well, the minus symbol is used in more than one way, and it does not always mean negative. It can mean just the opposite of something. And in the context of exponents, what that's intended to mean is we have the opposite of multiplication, which is division. So also, if you had like 2 to the -2 power, well, that's 1 over 2 squared, 2 times 2, okay? And the negative tells you that you are actually dividing, and the 2 tells you how many of them. Okay, so you can have negative exponents and they mean that you're actually dividing. You can also have fractional exponents, but I don't want to worry about that right now. That's something we'll talk about more later. So when you have a negative exponent, that means you really kind of have a fraction. But also, if you have a fraction, it means you really kind of have an exponent. So over here, there's more than one way to solve this equation, but I think that the quickest way to get started is to recognize that you can write this expression using an exponent rather than a fraction. So I'll have 7 to the -5n power times 7 to the -1 power. The negative means, well, really, we're dividing the 7. Okay, so I can turn a fraction into a negative exponent, or I can turn a negative exponent into a fraction. They're interchangeable. And it's not that one is simpler or better than the other. It's just that they're the same thing. And if you've got an expression with a fraction in it, and you've got other expressions with exponents in them, you might want to convert everything to an exponent format in order to start combining things. Okay, and then the right-hand side for now will just stay as it is. So equals 7, 6n plus 3. There's another property of exponents we need here. You might notice that we're multiplying 7 to some power times 7 to some other power. When I'll skip the reasons, which we could go into more detail if anyone needs to in a Zoom call. When you're multiplying two expressions that are exponential or have exponents, and the bases are the same, and then the exponents are different, you can add the exponents together and turn this into a single exponential expression. So this left-hand side can be rewritten as 7 to the -5n power minus 1. Just add the two exponents together, okay? And again, there's underlying reasons for that, but I don't want to go off on for 20 minutes on each one of these, explaining all the reasons for everything. So the next thing is, and I think this might benefit from an example. So let's go off to a sidebar here. Let's say you had something like 2 squared equals 2 cubed, right? 4 equals 8 is clearly wrong. It's just not equal, right? So if you have something like 2 squared equals 2 to the x power, well, x can't be 3, because that would be like saying 4 equals 8. And x can't be 4, because that would be like 4 equals 16. X can't be 0, because that would be like 4 equals 1. So what we can conclude is, if the bases are the same in an equation like this, you got 2 to some power equals 2 to some power, right? Those exponents have to be equal. There's no way for them to be different. X has to be 2, because otherwise you're going to say 4 equals 8, and that doesn't work. So over here, we can do the same thing. This exponent here has to be equal to this exponent here, because if they were different, you'd have like 7 to the 5th equals 7 to the 9th. But they don't. The 7 to different powers are different results, right? So these exponents have to be equal. So I just kind of throw them away and make an equation with the exponents. The base of 7 does not contribute to the solution, right? If that 7 were like a 9 or a 2 or a 12, it wouldn't affect your answer. The 7 just has nothing to do with the result, basically. Anyway, so now we can solve this equation, right? Like I can subtract 6n on both sides, and I'll assume that that's okay for everyone. Again, I could go on for 10 to 15 minutes for each thing here and explain in very great detail, and then most of you will stop watching the video pretty quickly, right? Because I'll be talking about stuff you already know. So I'm trying to skip things that you might already know, and then we can go over them in one-on-one hours if needed. I'm sorry if I keep saying that. I'll try to avoid repeating that so much. Anyway, now I can add 1 to both sides. So I get negative 11n equals 4, and then I can divide negative 11 on both sides. So n equals 4 over negative 11, or in other words, negative 4 over 11. This minus sign can go on the top, in front, or on bottom. It doesn't really matter. And if I want to, I'm not going to bother in this case, but if I want to, I can take this number and go plug it back in and make sure that it really does solve the original equation. What you might recall from algebra class is that sometimes that checking is actually a required part of the method of solving the problem. For this type, it is not. So we can check if we want to be careful, but it's not like it's an essential step in the problem. All right, moving along. Logarithmic equations. So now this type of equation, we do have to check our solution. We'll talk about why in a minute. So I'm just going to not talk about reasons so much for logarithms. I'll just talk about the properties more. And again, ask for help if you need clarity on the reasons. So when you are adding 2 logarithms that are the same base, these are both base 10 logarithm, okay? When you're adding 2 logarithms of the same base, you can multiply the arguments together. The argument is the stuff in parentheses, the stuff that is the input for the log. So in this case, I can rewrite this as log of x times x plus 1. Oh, sorry, struggling with the iPad here. Okay, equals log of 6, right? When you have an equation like this, much like with the prior one where we had 7 to some power equals 7 to some power, and the 7s, we could just throw them away. When you have some log equals some log, and the left-hand side is a single logarithm, right? We've got just log of some stuff and log of some stuff. When you have that, you can throw away the logarithms. They don't help solve the problem. They're just sort of an impediment. So the fact that we have log base 10 as our logarithm, the 10 doesn't affect the result, so we just throw it away. Okay? Again, for reasons. So now I can solve this equation. So basically, long story short, I'm going to move the 6 to the other side, but I'm also going to distribute on the left. So this x I'll distribute onto the x inside and to the plus 1. So I'll have x squared plus x equals 6. Then I'll subtract 6 on both sides. This isn't the only way to solve it, but maybe for this one, it might be the easiest. And this one I chose so that it factors relatively easily. So this is x minus 2 times x plus 3. And again, if you need help with factoring, office hours. So then x minus 2 equals 0, or x plus 3 equals 0. Okay, and then you solve each equation separately. So for this one, I'll add 2 to both sides. And then for this one, I'll subtract 3. That's supposed to be 0, sorry. Yeah, okay. That on this one, then we'll subtract 3 on both sides. Okay, so we get 2 numbers. We get x equals 2 and x equals negative 3. Now with this type of equation, when you do this step, of throwing out the logs, you maybe introduce what are called extraneous solutions. Maybe we're adding extraneous solutions. What that means is that the numbers that are solutions to this equation might not be solutions to this equation. Okay, when you're doing algebra, every step of the way, much of algebra is like one way to say is that they're reversible. So the steps you move to go forward in the problem or down the page, they're all reversible, and that you can just as equally justifiably do the steps in the opposite direction. Okay, when you have a step like this, it doesn't go both ways, where these equations are all equivalent. Up here, these equations are all equivalent. They are all the same equation. We're just shuffling symbols around, and going from here to here does not introduce extra possible solutions because of the way exponential functions work. We're skipping details. I should probably be more careful from here to here. This step does not introduce extraneous solutions because of the way that the exponential functions work. This one, though, this one does, so we have to be careful. So going back to the original equation, what you can do is you can take 2 and plug it into both sides, or wherever there's an x, I should say, and check that you really get a solution that actually works. That's one way to do it. Another way is the following, and I'm going to copy the equation down here so that we can zoom in on it. Put it here. And this is one of the reasons we talked about domain earlier, because domain comes up again. So remember that for any logarithm, the domain of log base b, whatever base of x, okay, this is 0 to infinity. You can't plug in a negative into a logarithm. You can't plug in 0 into a logarithm. It doesn't work for reasons that we could talk more about if anyone needs to. So here, if you plug in 2, oh, that's okay. You plug in 2, no domain issues, right? Here, you plug in 2, right, to this x. Sure, log of 3, no domain issues. That's fine. So this one checks out as far as the domain goes. Well, when you plug this one in, oh, now we get a problem. You can't have log of -3. So it's actually this one that is an extraneous solution. So you don't need to plug in your potential answers and total things up and check that it really is a solution. I mean, you can do that, but what you need to do is check that you don't run into domain issues, because this step here, this step right here, this introduced -3 as a possible solution that doesn't belong to the earlier parts of the problem. Okay, the 2 was a solution all along. The -3 got put there by that step. So we have to check for extraneous solutions, and so our only solution is x equals 2. So 2 is the solution to the equation. Okay. And again, I'm skipping some stuff here, some technicalities and details that we won't necessarily need all the time, but if you've got questions, just ask them and we can clarify. All right, what's next? I think I'm almost done here. Find the intercepts of a function. Okay, cool. So talk about conceptually just a little bit. If you have a graph of a function, and I'll just make something generic. I'm not going to try to match the one that's there on the page or screen or whatever. If you have something like, I don't know, like that, some function like that. Okay. So this crosses the y-axis here. So the ordered pair there is going to be 0, some y value. But x is definitely 0 because we're on the y-axis. Okay. So when you have an equation and you want to find out what's the y-intercept, well, if you plug in 0 for x and solve for y, you'll find that number. And you should only get 1 for a function. Here, we've got 2 places where the graph touches the x-axis. So like this will be some x value, whatever it might be, x1, I'll call it, and then 0 is the y-coordinate, and then this one will be some x value, call it x2, and 0 is the y-coordinate. So if you have an equation and you want to find the x-intercepts, you plug in 0 for y, and then you solve the equation, and maybe you get more than 1, you'll find the numerical x-intercepts from that. Okay, so that's what we're going to do. So over here, I want to find the y-intercept. Sorry, I'm zooming in and out quickly. So for the y-intercept, I'm just going to plug in 0 into the function because x is 0 at the y-intercept. In this case, since I have this quadratic function in descending order, in general form, the last coefficient is always going to be a y-intercept if you've got a polynomial in the general descending order form. Okay. Now, if I want the x-intercepts, I have to plug in 0 for y. So I'm saying, oh, well, 0 is the outcome of the function. And then this one I chose, again, to factor in a relatively easy way. So 3x. I guess that's minus 2. X plus 1. I'm sort of doing guess and check. So these multiply negative 2x. These multiply plus 3x. Negative 2x plus 3x is positive x. So yeah, that checks out. So I was just sort of doing a guess and check and quickly factoring. If factoring is something that you struggle a bit with, definitely email. We'll get on Zoom, help you figure it out. Okay, so that means that either 0 equals 3x minus 2 or 0 equals x plus 1. So here we'll add 2 to both sides and then divide by 3. So 2/3 equals x. And then here we'll subtract 1. So negative 1 equals x. So they're my two x-intercepts. So we get one y-intercept, and then we get two x-intercepts. Okay. Sometimes you'll get 1, sometimes you'll get none. You might get 3. You could get 5, I suppose. That would be messy, but it could happen. Yeah, so that's finding intercepts. And the overall thing is the same. Whenever you're looking for y-intercepts, plug in 0 for x. Whenever you're looking for x-intercepts, plug in 0 for y. What you do from there depends, but that's the starting point. Okay, what's next? Is there a next? There is. Is this the last thing? This is the last thing. Okay, here's the last one. We're almost done. Find the domain of a rational function. So we talked about domain earlier, and we did that one where we did 2x squared divided by x, the square root of x plus 6, I believe, is what it was. So just sort of reprising that, whenever you want the domain of a rational function, basically, you look at the bottom and set that equal to 0 and look for, okay, what would make the bottom 0? Because that's what's not going to work, right? Because you can't divide by 0. So whatever would make the bottom be 0, those aren't in the domain. So I usually write like this. I just write 0 equals whatever the bottom is. If you want, you could put not equals to emphasize we're looking for what doesn't work. That's up to you. It doesn't, I don't think it really matters that much, but I'm just going to say 0 equals. For me, that's what I'm used to. If you put not, that's okay. Okay, so 0 equals x minus 2 or 0 equals x plus 1. Here we'll add 2 to both sides. And here we'll add negative 1 to both sides. Or in other words, subtract 1 on both sides. So these are the two numbers that don't work in that function. And for a rational function, this is the only thing you have to check for. You don't have to worry about, well, what if the top is 0? No, that's not going to be a domain issue. If the top is 0, that's fine, right? If you plug in 1, like f of 1, well, you'll have 1 minus 1, right, which is 0 on top. And on bottom, you'll have 1 minus 2, which is negative 1, times 1 plus 1, which is 2. So you get 0 as a result. So the top being 0 is fine. That doesn't affect the domain. So what I want to do is I have my two numbers that are not included in the domain. So I want to write an interval format, probably, what that is. So we're going to start at negative infinity. We're going to go up to negative 1, okay? And then union negative 1 up to 2, union 2 up to infinity. So basically, I'm saying start at negative infinity, go all the way to infinity, include everything, but skip over negative 1 and skip over positive 2. That's what that's saying. Anyway, that's basically it. That's the review material in a nutshell. That's all the most important stuff that we're going to need to use again later for the class. So hopefully that was helpful, made a lot of sense. And yeah, again, as I've said more than once, if you need assistance with the homework, or you don't understand concepts, or just anything, just email me and I'll help you figure things out. Thanks for listening all the way to the end.